Good morning, everybody. Can you hear me? Well, Sunday morning, when I got this morning, it was a beautiful Sunday morning. I've not been out for an hour, so I don't know now, but back home in the UK, I live in a late 18th, 19th century great room listed building. My neighbour is a church. I think it dates from the 17th, 18th century, something like that. It's a beautiful church. It's a light grey, whitish stone-built building with a steeple. And every Sunday morning, around about 9 o'clock, there's a peal of bells rings out. It does something like this. Ding, 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 dong. Ding, 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 dong. So, sometimes on a Sunday morning I sit sipping coffee and I think to myself, there's something missing here. Now, is it the fact that they've not got a bell to make it go ding, 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 or there's somebody not turned up in the bell ringing team? Always amuses me. However, I'm also mindful this Sunday, back in the UK, is Armistice Sunday. I know in the US you remember the fallen on Veterans Day, but across Europe and the UK it's Remembrance Sunday. So I'm just mindful that today we should just remember them that made the ultimate sacrifice so that we can be here today. So, I have an apology to make in that at the last lecture I couldn't get this gizmo thing to work. And I'm quite embarrassed to say that being an electrical engineer, I forgot to switch it on. But it's quite powerful, this thing. It's a bit like Harry Potter's wand, because if you go like that, see? But I also have another apology to make, is that I couldn't remember the field of research of this guy, Richard Feynman. And I like this. This is a quote of Feynman. I mean, you can read it for yourself, but it does make sense to me. Now, Richard Feynman's field of research was quantum mechanics. And quantum mechanics is the study of things very, very small, atomic particles. So we're not talking about electrons, neutrons, protons. We're talking about things much smaller than that, which are things referred to as quarks, or mesons, bosons, Higgs bosons, things like that, and their interaction. It becomes very statistical, because you can't see the things, but that's quite different from these guys. Isaac Newton, Albert Einstein, Stephen Hawking. They studied the things at the other extreme, which would be the universe, the big massive. Isaac Newton, born in Grantham, not far from where I live in Retford in Nottinghamshire. Theory of gravity, yeah? Albert Einstein, the German physicist, theory of relativity. Stephen Hawking, Lucasian professor of mathematics when he was there. Big Bang theory. I went to a lecture by Stephen Hawking. He presented a lecture when he was releasing one of his books. Went down to London. I have to admit, I didn't understand anything about it. But what intrigued me was the lecture itself. At the beginning of the lecture, he came on in his motorised wheelchair, positioned himself, say where I am, so you could see the screen. And he started to talk in that distinctive electronic voice, yeah, that we all know of Stephen Hawking. And he had a PowerPoint presentation like I have. So he spoke for 2 minutes with his first slide, and then it went quiet. And then it extended into more quiet, and you're thinking, something's gone wrong here, because his battery's gone flat, something like that. Anyway, after 2, 3, 4 minutes, the slide changed and he started to speak again. And it went on like this. And I think we're all aware that Stephen Hawking suffered from a motor neuron disease, which disables his physical movements and things like that, but his mind was very active. And if you watched him closely, you could see that his cheekbone was moving. And what he was actually doing, he was just typing in the text or his voice for the next slide. And I thought that was wonderful, that, because respectfully, he could have typed all this in before he even came into the lecture, just hit a button and away he went. But he gave us the respect that he wanted to present the lecture to us as he wanted us to hear it, and I thought that was wonderful. So, we digress. This is the third talk of 7. I apologise if anybody turned up yesterday for this talk, as I did. We got the schedules a little bit skewed with, but anyway. So, this is number 3, bits and pieces. And today we're going to do a forensic investigation. Yeah. And at the end of our forensic investigation, we're going to talk about how we present this evidence in a report form, what happens with that report, and eventually what we have to do in court. So, in the beginning, now this is relevant to what we're going to talk to today. I'm going to take you back to 1975. As a young apprentice engineer, coming from British Steel Corporation, on a Friday night, I was at the local technical college. Being an apprentice engineer, we used to go to a training centre where we were taught all the vocational parts of being an engineer. But once a week, we were sent to the local technical college to learn the theoretical part. And our particular day was a Friday. So we were there all Friday, and then it extended into Friday evening. Now, being young lads, Friday evening was important to us because it's the end of the week. You want to be out having a few beers and having a few smokes and a laugh and chasing girls like that. But we were stuck in the laboratory. And the laboratory was in the bowels of this Victorian college. And the lecturer was an old mining engineer, and he knew what we wanted to be doing. So he set up this demonstration. And what he got was, he got a light bulb in a light socket, and out of that he got 2 pieces of electrical cable. And the cable was clear, its plastic was clear, and you could translucent, you could see the copper conductors inside it. And to that, he got it connected to a fuse and then an electrical supply. So when he switched the electrical supply on, the light bulb lit up, which it should do. Yeah. What also he'd done is near to the light bulb, he'd stripped away some of the plastic insulation. So what he did is we're going back to incandescent bulbs then, it was a bit warm, so he got a cloth and he got hold of the bulb and he twisted it. And the 2 wires touched each other. And what happened was, the fuse blew and the light went down. And us being young lads, we thought, so what? So what he did then is, out of his pocket, he took a nail and he opened the fuse up and he inserted the nail. Parted the wires, switched the power on again, the lamp lit. Did exactly the same, he twisted the bulb and the 2 wires touched. And at first nothing happened. But then, if you watch the wire, it starts to glow a deep red rose colour. Then it brightened into orange, then it brightened into white, then there was a flash, and then all of a sudden the plastic insulation went up in a cloud of smoke, the bulb went off, and the wire disintegrated, charred. We all went, wow. Now, I don't know if that was a defining moment in my career or a divine moment, I don't know, but it always struck me that. So, and it's relevant to what we're going to talk about today. So I do apologise, but we do have to introduce a little bit of maths. And it's very simple maths, and I'll guide you through it slowly. So, let's see if this thing's working. Yeah, here we've got 3 parameters of electrical engineering. If you can imagine this thing is an electrical conductor. And we've got this guy, Mr. Volt, who is the guy who provides the pressure, the impetus, to push Mr. Current through the conductor. Yeah? And this guy, Mr. Ohm, or Mr. Resistance, is preventing current flowing in this conductor. I always liken this to a hose pipe with water in. If water's flowing through a hose pipe, it's being pushed by pressure. And the water flow, the pressure represents voltage, the water flow represents current. And if I were to press on the hose pipe, the current would reduce and my force must be resistant. Yeah? And there's an interrelationship between these 3 parameters. Here, voltage equals current times resistance, resistance equals voltage times divided by current, current equals voltage divided by resistance. Those 3 little equations are Ohm's law. Yeah? So, if we consider a simple space heater, an electrical heater, and it's rated at 2 kilowatts, which is 2,000 watts. Yeah? We see these every day in our houses or whatever. Now, electrical power is equal to volts times amps. So, if we arrange that formula there, if you agree with me, amperes equals power divided by voltage. And in a UK system, where we use 230 volts, if we divide 2,000 watts by 230, gives a current of 8.7 amps. Yeah? And if it's a US system, where we use 120 volts, that translates to 16.67 amps. Do you agree? Yep. Now, also, if we substitute some of those former equations into this power one here, we get I times R equals IR squared. I've done it here on the bottom. Yeah? P equals VI. We know V equals IR. So if we substitute V in there, it becomes that IR squared. Now that's important because IR squared is the amount of heat dependent on current and resistance that's generated in an electrical wire. Okay? So, in a normal sense, normal sense, there's 2 forms of electrical fire ignition phenomena. One is referred to as Joule heating. So if you've used a toaster in the restaurant today, or if you've dried your hair with a hairdryer, if you're ironed your trousers like I've been with an iron, you're utilising the Joule heating phenomena. Yeah? Utilising it in a controlled way. What that means is, as electrical engineers, we can do calculations and set specifications of electrical systems, so Joule heating becomes of a benefit for us rather than something that's uncontrolled. Now, in industry, we get circumstances where, well, not only industry, everywhere, where we get uncontrolled dual heating, like this. Oops. Like this. So this is a bolt that's clamping down an electrical cable. And what's happened here is this bolt may have become loose, or the electrical terminal itself may have not been soundly made off. It might be loose or whatever. So at that point there, the electrical resistance has increased, and through that, the heating phenomenon, the joule heating has also increased, and you can see it's glowing red. Engineers, as a maintenance practice, go around all their control panels on a monthly, 2 monthly, whatever period, and they use an infrared camera. And this is a picture of I think it's a contactor or a relay. And they take pictures, and you can see here, this particular connection is loose. So it's hotter than the other two. What's the consequences of that? One is the losing energy, because it's going away as heat, and the other one is there's a potential of a fire, and if there's a fire, the process that it's controlling shuts down and there's a loss. So it's of benefit to do a thermographic survey. Okay? The other fire ignition phenomena is a thing called electrical arcing, and you may have seen this at home, particularly if you've unplugged hair dryers or something that's of a heating appliance. It will flash when you pull it out. That is electrical arcing, and that's where the air has become ionized and it's become an electrical conductor, and it's depicted as a blue-white flash, and it is of immense temperature. We're talking 20,000 degrees C, so it's like electrical storm lighting. Okay. So going back to the heater, we know it's 2,000 watts, 2 kilowatts, and we know through our little calculations, at 230 volts it's going to draw 8.7 amps, and at 120 volts it's going to draw 16.67 amps. So in a safety sense, to protect ourselves and protect that if a fault occurred, we put these little things in. Fuses. And fuses are just pieces of cylindrical wire. Most often it's tinned copper wire, or it can be silver. And if you're really posh, it might be gold, but I don't know. But anyway, my particular research field was in electrical fuses, so we're looking at the disintegration of fuse wires. So I'm going to draw a graph now, and we're going to work together on this. So on the x-axis, we've got time in seconds. So here at the intersection is now, and down there is the future. And up on this y-axis we've got temperature in degrees C. So here we've got the melting point in temperature of the fuse element. And I'm going to apply some electrical current now. So as we go along in time, the temperature of the fuse element is constant until we get to this point here, where for some reason it starts to increase. And it keeps on increasing to this point here. What do we think happens at this point? Hello, yeah. We've got to the melting point of the fuse element. So at that point, the fuse element's gone from being a metallic substance, solid, to a liquid. So instead of having a piece of solid fuse wire, we're at the point of it becoming molten. So at that point there, some point of that fuse wire breaks. And in breaking, it interrupts the electrical current, ceases. That's what a fuse does, it's a sacrificial element. It protects the electrical system, it sacrifices itself. And what do? We take it out, throw it away, put a new one in. Or, if you're not conscious enough, you get a piece of cigarette silver paper and you wrap it round, or you get another nail and you put that in. I've done it, I admit it. The important thing here is this thing, time. And we're looking at the disintegration of this fuse, this piece of wire, in seconds, yeah? And I refer to it as the long time domain. So, we're going to change the parameters now. Oh, I'm just putting there, low rising electrical current. We're going to do the same, we're going to draw another time scale and another temperature scale, but this time we're looking at milliseconds. Yeah, so that's thousandths of a second. And this is the difference between the nature of electrical faults, that some can occur in the slow time domain, and some can occur in thousandths of a second. And we'll follow this through again. So we've got the melting point of the fuse element, we're injecting current, and then at this point here, we apply a fault, and electrical current rises. But it rises in a millionth of a second rather than in seconds. So we ask, what happens at this point here? Yeah? Medium rising electrical current and magnitude above the fusing limit, yeah? So all of a sudden it was woof. So what happens here is, because it's a magnitude faster, the whole fuse element transforms from being a solid into a liquid in millionths of a second. What we see of the fuse element itself is this, is the wire starts to form or starts to evolve spheroids, which we refer to as unduloids. So if you can see, there's little balls separating, and they're quite consistent in separation. In an evening, when you're watering the garden, and you're watering your geraniums or azaleas or whatever the lawn, if you've got a hose pipe on you, if you take the diffuser off the end, and you just stand there and you watch the column of water come out, at some point it'll form spheroids. Now this is what we refer to as the Rayleigh plateau effect. Yeah? And what's happening in that column of water, there's some forces being acted upon it, is one is that gravitational forces are acting on it because it's going down, but there's also surface tension forces around the column that's pulling it into spheroids. And that happens exactly the same in an electrical fuse, because we're looking at a column or a cylinder of molten metal. And we get these little unduloids forming. And as time progresses, what happens is it explodes. And you can see here these little balls, and these white areas are electrical arcing. So what happened is, between these electrical conductors, well, at that time, they're not now, but formerly were, the air has become an electrical conductor, and we formed electrical arcing. So basically, in the medium time domain, we get this explosion. So we're going to take it a little bit further now, and we're looking at time, this time, in microseconds. This is millionths of a second. And we'll add the axis again. So we've got the melting, and here we've got electrical current in orders of magnitude. Orders of magnitude. So if this current was, say, 10 amps, we're looking at it being 1,000 amps. Yeah? And the disintegration of the fuse element will be in millionths of a second now. Very difficult to understand what's going off, because normal cameras you can't take a picture of it. Even fast cine cameras you can't. I think we're just at the stage now where you can get ultra fast video cameras where you could. But what happens in this instance, and this is an X-ray of a fuse element, is we get an explosion. It's not a chance to form spheroids at all. It's just a shockwave electrical current going through a tube, and it's just exploded. But it's done it in a sort of like regimented fashion. So you can see at these areas, this is where it's actually, that was the fuse element through the middle, and that is where it's exploded. So we have an understanding from that how an electrical wire will disintegrate. Yeah. So what we're going to do now is we're going to look at a particular forensic investigation. And as an expert witness, forensic engineer, we can be instructed in different modes. In a civil case, we can either be instructed by the plaintiff claimant, or in Scotland they're referred to as a pursuer. I don't know why they do that in Scotland, but they do. If we were instructed for the defendant, obviously with the defendant, in Scotland they call it the defender. I'll just come to this criminal cases. In criminal cases, if we are instructed for the prosecution, in the UK, we're instructed for the Crown, King Charles III. I think in the US, correct me if I'm wrong, it's either, is it the state or federal legislation that is the prosecutor? Yeah? Either one, thank you. In some cases, we can be instructed as a joint expert, which means that we're not partisan to either side. We're instructed by the court because the court needs to understand the technicalities of this particular case. And usually, the judge in this instance will issue a court order. And on that court order, there may be questions, well there will be questions, that he will want a joint expert to answer so he can understand the circumstance in his language, in his mind, so he can determine the output of the case. Yeah? So, whoa, we've up a little bit. We're going to look at this particular case. Sorry. This involves a dishwasher. It also involves a clothes washer as well. This dishwasher was manufactured, sorry, it's not manufactured, it was distributed in the UK by a prominent appliance distributor. And this particular model of dishwasher, clothes washer, had a propensity to catch fire. And this came to light, I got called to Jaguar Land Rover in Birmingham. And the way Jaguar Land Rover works in Birmingham, I'm not saying this is the same everywhere, is that there's a long production line. And we have bits starting at one end, and we have Jaguar Land Rovers coming out at the other end. It's long. But spaces down the production line has to be fed with parts. And the parts are stored in a big store warehouse separate from the production line. So it's all computerized, and when a particular car of a particular specification gets to a point in the production line, the parts have come round from the store warehouse and they're there, so the car doesn't stop. And it's same all the way down the production line. Now, on this particular day, at the end of the day, the ladies who've been working in the restaurant for the store placed all the dirty dishcloths in the clothes washers. Clothes wash. And it caught fire. And it burnt down half the stores for Jaguar Land Rover. Now that has a massive insurance implication because Jaguar Land Rover production line stopped for 4 or 5 days. So there's no Jaguar Land Rovers coming off the end. And it caused them massive insurance loss. This is just by putting some dirty tea towels in a dishwasher. Not dishwasher, sorry, clothes washer. So, you get called in and you're faced with this type of thing. Where you can see that this is a dishwasher has degenerated into a mass of bits blackened with ash and whatever. And as an expert in this particular case, I think there was 4, maybe 5. So there'd be one for Jaguar Land Rover, there'd be one for the distributor seller of the appliance, and then there'd be other experts for the bits and pieces, the components that make up this particular dishwasher. And it's an orderly investigation in that we all go at the same time, and all the parts have been packaged up in plastic bags and sealed. They've got a special code on. We open them one by one, and then we get our hands and we start to look for things. And we were drawn to this thing. And you can see this lady scowling down there as if to say, "What's that?" Well, it's this thing. It's a water pump, but it pumps heated water. And it pumps it, well, around the dish, clothes wash, whatever it is. Now, part of that is this thing here. This is the heat element. So water would come in, it would circulate around here, heated electrically using joule heating, and then it could exit. Yeah? Does that make sense? So, there were lots of these fires, so we've just not got one heat pump to go on, we've got quite a few. Some of them, quite a few of them, showed these traits. So, here's the heating element, here's the cover, the thin metallic cover which would go over it, and at this point you can see something's occurred. That would be in line with that, and that's electrical arcing, the effects of electrical arcing. Well, the rust on it is caused by the moisture atmosphere and the warmth and things like that, but the whole is due to electrical arcing. Now, what we did is we took x-rays of this heat pump, and we were interested in this area here. And this is it enlarged. And I was drawn to it because you can see here these little spheroids that were once metallic conductor. Here. Yeah. So that indicates to me as a forensic engineer that this fault's been introduced in the medium time domain. The metallic component has been allowed to flow, and it's through surface tension forces it's gone together and joined and formed a spheroid. So we will remove the top now, and we can see this area here, which is electrical arcing. We can also see here that this electrical component is delaminated from this structure where water passes matters around. Now this has been designed that the water, although the heating element is heating the water is controlling the temperature of this heating element. And when it's delaminated, it's not controlling the heat of this element. It's actually allowing it to increase in heat more than it should do. And in doing that, it's caused the wire inside it to disintegrate and melt. So, of all the people interested in this case, it then focused on the manufacturer of the heating element and whoever connected it to this as the principal culpable party for the cause of these failures. So, what do we do with this information that we've gathered from this investigation? Well, first of all, we have to write a report. And the report in the UK has to conform to certain procedural rules. There's a lot of these rules, and number 35 in a civil case here is Civil Procedural Rule 35 for expert witnesses. And so at the header forward of every report, we have to put a statement of truth, which basically says everything within this report comes from me, nobody else. These are my opinions, these are my truthful opinions on which I express myself. That's always there. Sorry. In a CPR 19, which is a criminal matter, because respectfully it's a little bit more, I won't say important, but it's more intense. The declaration becomes a lot more intense as well. There's a lot more things we have to conform to. Sorry. And we start off declaration, and there you have it in its full glory. My middle name, Ernest. If anybody's called Ernest in here, I apologise, but I don't like it. I think it would be better if he said Elton. I'll wait. So that's in a CPR 19 format. Within the body of report, we put an affidavit, which then compounds and it extends the truthfulness of the report. And within the body of the report then, we write our observations, what evidence we've seen, and we draw it all together to produce a conclusion. But the way I do it is, at the heading of the report, I introduce what I've been told about it. So if a solicitor said this, they said that, then I put that down. And then, if there's any technical matters that I think the court needs to consider, I will explain them, because that introduces understanding. And then I always aim to introduce evidence in a structured way so it builds and builds and builds to the argument that I want to present in the conclusions. And the report will end in a conclusion. So this one is in a civil matter, and I redacted it obviously for confidentiality purposes. But given what we've said in previous lectures, there's a key word there on the balance of probabilities. So I've drawn my conclusions based on the weight of evidence that on the balance of probabilities in a particular circumstance that occurred. In a criminal matter, this is a conclusion. This happens to be for a breath test procedure. And once again, I draw on this beyond all reasonable doubt. And there's a key word in there. There is a possibility that the analysis, blah, blah, blah. So in my report, I am clear in my mind that there is a possibility it could have interfered or something like that. It's important. Also within the report, I have to use references. I can't just pick information from anywhere. I have to use peer-reviewed references of information or research which are accepted in the public and academic and legal domain as, well, they're accepted as good evidence. So, there's a body of references. In this case, there's a load, but I always put a number in it. So, in the narrative of the report, anything in black, brackets, parenthesis, with a number one draws the judge to look at that particular reference. Yeah? I also put in a glossary of technical terms to help the judge or whoever's reading it. So if there's a particular thing that I think needs more expression, more understanding, I'll explain it in further depth in the glossary of technical terms. Always within a report you have to put your credentials to act as an expert witness. So I put my CV in there. Awful picture of me. Gives my expert credentials. And further down it will go into my qualifications and experience and, like this one, case history. It's important in any matter that an expert witness should have a case history. Obviously, when you first start doing that, you've got no case history at all. But that's the bullet you have to bite, you have to build it up. And I present it in a way that it shows a number of cases, active for claimant or defendant, criminal, civil, private instructions we sometimes get in this single joint expert. And then these are the court cases, and there's some beneath this. So that supports my credibility to be an expert witness. So what do we do next with an expert report? Well, when two experts are, one's assigned to a claimant and the other one's assigned to the defendant, we submit our report and they're exchanged. So one guy will get my report, and I'll get his report, and we'll read through it, and I'll think, well, that's a load of rubbish. I'm not seeing that. And he's probably thinking, same to me, that's a load of rubbish. I don't agree with that. But then in the court procedure, it's stipulated that we have to meet. So we can either do this by Zoom, or I like to do it personal, so I'm sat across the table and we can take time to discuss these things. And the aim of that is we need to find points of agreement and disagreement to help the court in its deliberations. Now these meetings become very intense because it's just me and somebody else, and they become very responsible. The legal, if there's any solicitors, lawyers in here, I'm sorry, but the legal profession at this point should have no input at all. They shouldn't be saying to us, you should say this, you should say that, or counter that, counter that. It's just me and the other guy. And from that, we have to generate a joint expert statement, which will then go to the judge in the court and he gives our opinions. It becomes like a game of chess. And it is a game of words. That if one expert in a joint statement says something, I might have to counter it with something else. Not but I say this, he says that. And as you can imagine, if it's a fatality, we're talking about someone's death. If it's a criminal matter where somebody's liberty is at stake, it becomes very intense. It could be a massive £1 million loss, where somebody might have to pay out millions of pounds. And it all comes down to words. I remember one of the very first cases I did was for a water company, once again, who were being criminally charged for discharging sewage effluent illegally. And this time there were two experts on our side and there were two experts on the other. And we met together and we discussed this matter. And then we started to generate a report. And unbeknown to me, because I was rather ignorant at this stage, I allowed the legals to direct me in what I should be saying. And this report ended up being 72 pages long. Because we were at it for about 2, 3, 4 weeks, we kept sending it back, and they kept altering it, okay. Now, to a judge, that's no good. He's not going to sit and read 72 pages of argument. What he wants is a succinct thing that says, this is the points we agree on, this is the points that we disagree on. So in this particular case, I think the judge might have thrown it in the bin and said, insurance companies sort it out, which they did in a week. And that was a case settled out of court. So, at the point that we've got a joint statement, we go to court. And we sit there as experts at the back of the court. Sometimes we're allowed to listen to the court proceedings from the very outset. Sometimes we have to sit outside in the lobby and be called into court at a pertinent time. But this is when it gets really intense, because cross-examination is another level of a chess game, because it's me against an advocate. And I always go into these situations with a certain mindset that says, look mate, I know more about electrical engineering than you do. And it's a battle, but it's always very, very interesting. And I'll talk in some of the later presentations about some of these interactions. Some can be intense, some can be amusing. So, that concludes this presentation today. Does anybody have any questions?
Just one. Have you ever been involved in a case, you see it often where people will jump a fuse, bypass a fuse with a bigger gauge wire, or they'll put a penny or some stupid thing in behind the fuse?
Yes. The gentleman was asking, have I ever come across cases where people have bypassed fuses by putting a penny in, or like a nail, or anything like that? Yes. I was called down to a case of a car wash in London, and appropriately named Mr. Bubbles. And this particular car wash, and I say with this respect, was operated by Eastern Europeans. And unfortunately, what they'd done, because the fuse kept tripping, they wrapped, I'll show you a picture of this at the next lecture, but they wrapped electrical cable around the terminal pins of the fuse, holder, pushed it in. The guys who were operating the car wash lived in the back of the premises, so there was a kitchen, sleeping area, and there were also washing facilities, including an electrical shower. Guys in the shower. Did I go any further? Tragic. Criminal matter. And there are other ones where there's been flagrant breaches of electrical regulations, things like that. Any more questions? Right. So, I don't think this is correct, because we had a little bit of confusion yesterday whether we got 6 presentations or 7. So in the course of things, I did this yesterday and I apologise, I think this is the one after next. I think tomorrow's, not tomorrow, the day after tomorrow, is about intellectual white collar crime. So we come into fraud and stealing people's intellectual property and things like that. So that's presentation 5. Day after tomorrow is presentation 4. And that's it. Thank you for your attention. I'm really pleased that you've come. I enjoy your day. And make sure you're on the ship.